Hello everyone and welcome to your Chem 113 review on oxidation numbers. My name is Jason and I work for the ASU Tutoring Centers. Okay, so oxidation numbers can represent one of two things. They either represent the actual charge of a species or of an element, I guess, in a compound. So for instance, if you have like, you know, an ionic compound, I keep forgetting the name ionic compound today. If you have an ionic compound such as sodium chloride, we know if we were to break this apart, it's Na plus and a Cl minus. So we would say the oxidation number of sodium in this compound is +1 and of chlorine is -1, because those are the charges of the actual ions. However, this doesn't always work, right? Especially imagine thinking about polyatomic ions. If you have the polyatomic ion sulfate, SO4, 2-, what's the charge of sulfur here? Well, in reality, sulfur here doesn't exactly have a charge, right? It's the entire species that's charged. The sulfur doesn't actually have a charge itself. So in that context, we have to think about oxidation numbers as being more of a theoretical charge. So that's the second way you can think about oxidation numbers. It's sort of a theoretical charge of a species. So in the context of, it typically shows up in the context of like polyatomic ions, trying to decide what a piece of the polyatomic ion, what its charge is. Now this becomes useful in redox reactions, which I'll tell you what a redox reaction is. Redox stands for reduction oxidation reaction. And essentially, with a redox reaction, electrons get transferred. Are transferred. So from like one species to another species. And using oxidation numbers, we're able to keep track of that to have an idea of where the reactions are, where the electrons are coming from and where they're going, what species is being reduced, what species is being oxidized. We won't get into that. That'll be later on, that we'll get into the specifics of it. But so today we're going to talk about how to find the oxidation state of different compounds, okay? So in each of these, we're trying to find the oxidation state or the oxidation number of sulfur, okay? So let's look at the first one. So the first rule of oxidation states, first rule, I guess I'll keep track of the rules in one space. I'll keep track of everything else in another. So maybe I'll put rules here. Some atoms, or some elements, I guess, almost always have the same charge. Almost always have the same oxidation state. So for instance, oxygen is almost always a -2. Put my colon there, yeah. Hydrogen is almost always +1. Now, it's not a steadfast rule. It's just a good rule of thumb. So hydrogen pretty much always has a +1 unless it's bonded to a metal. If it's bonded to a metal, it has a -1. So it has +1 when it's non-metal, and it has a -1 when it's bonded to a metal. In that state, it's called a hydride. Oxygen always has -2 charge, except for peroxide, except when it's in peroxide. And peroxide is O2, 2-. So in this state, it has a -1 charge, right? Because there's two oxygens. So if it has a -1, -1, that gives it the overall charge of -2. So oxygen is always -2, except for peroxides. Hydrogen's +1 for nonmetals, -1 for metals. okay, if it's bonded to nonmetals and bonded to metals. So let's look at the example we have here. The example we have here, A, is H2S. Sulfur is a nonmetal. So in this case, hydrogen would have a +1 charge. So on the left-hand side, we have a +1 and a +1. We have two hydrogens. So overall, the species is uncharged, right? There's no charge over the whole thing. So if we have +1 +1, what must the charge of sulfur be? Well, +1 +1 is +2. So in order to be uncharged, sulfur must have a -2. Okay. So the answer to this first one is -2. Okay, let's move on. The second one, the only thing here is sulfur. So this is going to bring up a second rule that we're going to use. And that's that the oxidation numbers have to add up to the overall oxidation number of the species. Okay, the overall charge of the species. So if you add up oxidation states, which is another term for oxidation numbers, you get the charge of the whole compound. And we did that, we used this idea up here in part A, right? We said the overall charge is 0. The hydrogens give us a +2, so that means the sulfur must give us a -2. We use that idea here. So in this case, for part B, if they must all add up to be 0, well, what number added up 8 times is 0? The only number is 0. So the oxidation number must be 0. And this sort of gives us another sort of general rule, is that anytime you have sort of what is called an elemental form of an atom, and an elemental form just means it's the only element in your atom. Okay, so like in this case, we have S8. The only element in here is sulfur, so it's elemental. It is elemental sulfur. Elemental forms of atoms give oxidation numbers of 0. Because of the reason we just described, right? You have S8, they all have to add up to be 0. The only way that's possible is if each individual one is 0. So sulfur has to have a charge of 0. Okay. So now let's just sort of apply those general rules that we have to part C. So as I mentioned, some elements always have the same oxidation state. This also applies for sodium in this case. The oxidation number of most monoatomic ions equals the charge of the ion. That's pretty much the most important rule. I'm going to put it, I guess I'll put it over here. Cool. Rule number 4, the oxidation number of monoatomic ions equals their charge. And I alluded to this earlier, right? I was talking about the weird cases tend to be the polyatomic ions when you're trying to find those oxidation states. But in the case of monoatomic ions, like for instance here, the sodium ion is monoatomic, we know exactly what its oxidation state is. It's exactly the charge. So the charge of sodium is +1, it's in the first group, okay? And as we mentioned, oxygen also typically has a charge of -2, unless it's in peroxide. So if we're trying to find the oxidation state of sulfur, let me call the oxidation state X. So what we have right now is we have 2 positive 1s, and then we can add the charge of sulfur to it, which is X. And then we have 3 negative 2s, that comes from the oxygen. And overall, the charge of sodium sulfite is 0. So when we add up all of these oxidation states, the 2 plus 1s, the X, and the 3 minus 2s, we get 0. So we can simplify this. 2 minus 6 is -4, which tells us the oxidation state of sulfur in this case is +4. I guess I'll change it to purple. Keep true to what we're doing. +4. Okay. So that's probably the biggest rule of all of these rules. I mean, they're all important, but rule number 4, that oxidation number of monoatomic ions equals their charge, is almost the most important one. So the real power of these oxidation states comes in the polyatomic ions, getting the oxidation state of the species within the polyatomic ions. Okay. Well, thank you for watching. As I mentioned, I work for the ASU Tutoring Centers. If you want more information about the tutoring services available on all 4 major ASU campuses and online, please check out tutoring.asu.edu/content/tutor-search. If you go there, you'll be able to find a tutor at whichever campus you're on or online that'll be able to help you with your specific course. Thank you again for watching, and I hope you have a wonderful day.